This is Calculus 12, Chapter 4.2. Recall the intermediate value theorem that if f is continuous, then there exists a c between a and b such that f of a is less than f of c is less than f of b. And it is an existence theorem, so it doesn't say what the exact value is. Which brings us to the mean value theorem. If y equals f of x is continuous on the interval a to b and differentiable on the open interval a to b, then there exists a c between a and b such that the derivative at c is going to be equal to the average rate of change between a and b. This is also an existence theorem. And when we say mean, it's not the arithmetic average. We're looking at the average rate of change. This is more restrictive than the intermediate value theorem because it needs to be differentiable. But in this case, we can usually solve for c. So let's try to understand this theorem graphically. So the average rate of change is this. And the mean value theorem is not applicable here because we have the derivative here does not exist. This is a corner. And it needs to be differentiable on the whole interval. So it's differentiable here and here, but it's not differentiable there. Here, this is not applicable as well. And the reason is it's discontinuous. Okay, there's a jump discontinuity here. And the mean value theorem requires continuity. Okay, and that's the average rate of change. Here, the average rate of change is this. We do have continuity here, and we do have a smooth curve, so it's differentiable. So the mean value theorem applies. And we can see that we have a tangent here that matches this slope. Here, the average rate of change is this line, and we have continuity, we have a smooth curve, so it can be differentiable, so mean value theorem applies. And we see that we get a match roughly there and roughly there. So when you're answering questions that require the mean value theorem, you have to state whether it applies, and if it does not apply, state the reason why it does not apply. Okay, so here's some definitions. Increasing and decreasing functions. Let f be a function on an interval I, and we have x1 and x2 belonging to I, and x1 does not equal x2. So f is an increasing function on I if x1 is less than x2 and f of x1 is less than f of x2. Similarly, f is a decreasing function on I if x is less than x2 and f of x1 is greater than f of x2. So these are just definitions. And let's look at the corollary. Let f be continuous on a to b and differentiable on the open interval of a to b. So here we're not just talking about f of x1 and f of x2 and x1 and x2. We're looking at the derivative. So if the derivative is greater than 0 at each point between a and b, then f is increasing on a to b. If the derivative is less than 0 at each point between a and b, then f is decreasing on the whole interval a to b. So we start with the definition. Let x1 and x2 be in a to b such that x1 does not equal x2. And it's okay to include the endpoints here. And we're going to use the mean value theorem as well. So we're saying the derivative at c must exist, and it's going to be the average of f of x2 minus f of x1, all divided by x2 minus x1, for some c in between x1 and x2. Okay, let's rearrange this. We're going to move this over to the other side, so we have f prime of c times x2 minus x1 equals f of x2 minus f of x1. Now, what can we say about this as a number? Well, let's go back. x2 is always greater than x1. So this is positive. Let's look at this. F of x2 minus f of x1. F of x2 minus f of x1. This is bigger than this. So this is going to be positive, and it's increasing. So if this is increasing, this must be greater than 0. So 1 is true. So these two must match. If this is decreasing, f of x2 minus f of x1 is going to be less than 0. And we have this condition. So decreasing. So both of these must match. So if f of x1 is less than f of x2, then f prime is greater than 0 and f is increasing. Similarly, if it's greater than, then the derivative is less than 0 and f is decreasing. So the way we do the proofs is use some definitions, use some theorems, and try to show that it's true. So if we think about the IVT, what has to happen for an increasing function to be a decreasing function and vice versa? Well, there must be a point where the derivative equals 0. So there exists a c such that the derivative equals 0. So here we have some more corollaries. Functions with the derivative is equal to 0 are constant functions. So if f prime of x equals 0 on an interval I, then there exists a big C such that f of x equals c for all x in the interval. Okay, so it's going to be just a horizontal line. since the derivative is 0. Here's another corollary. Functions with the same derivative differ by a constant. So if the derivatives match at each point on the interval, then there exists a c, big C, such that f of x equals g of x plus this big C for all x on the interval. Okay, so here we have a function, here we have the derivative. Let's make up another function, and it's going to differ by a constant. Let's just make this 10. The derivative of this is still cos x. So we can see that it doesn't matter what constant we put in here, it's always going to be cos x. And this is an important point for our antiderivatives. So a function capital F of x is an antiderivative of a function f of x if the derivative of capital F equals lowercase f for all x in the domain of f. And this process of finding an antiderivative is called antidifferentiation. So let's look at an example of this. If we're given the derivative is equal to sine x, we need to think about which function will have a derivative of sine x. And you can just look at the tables. Cos x. And again, we can add any constant and the derivative will still be sine x. So you can think of this as having an infinite number of solutions. All we have to do is add the c. Here's one with a power. And to do this, we're going to do the backwards of a power. So let's start off with the power term. So when we take the derivative, the power is reduced by 1. So we need to increase the power by 1 when we're taking the antiderivative. Now, 4 times something must equal 8, and that's going to be 2. Are we done yet? No. We have to add the constant. So here we are working backwards on the power rule. Okay, let's look at another example. It's not an antiderivative. It's finding a solution for this function that satisfies the MVT. So the average rate of change is f of 4 minus f of 2, because that's the given interval, 4 minus 2. So we're taking ln of 4 minus 1, that's ln 3, minus ln 2 minus 1, so that's ln 1, over 4 minus 2, that's 2. Ln 1 is simply 0, so we have ln 3 over 2. That's our average rate of change. The derivative for ln is 1 over x, but our x is x minus 1, and if we multiply by using the chain rule, it's just multiplying by 1 because the derivative here is 1 and 0. So we just have 1 over x minus 1. And to find our c, 1 over c minus 1, this is our 1 over c minus 1, must equal this value, ln 3 over 2. We cross multiply, we get 2 is equal to c minus 1 ln 3. Now we want to isolate c, so we need to move ln 3 over to the other side. So c minus 1 equals 2 over ln 3. And we just need to do one last step. C is equal to 2 over ln 3 plus 1. This negative 1 becomes plus 1 on this side. And this is our solution. Next, we're given a piecewise function, and we're given an interval. So it's not differentiable at the join of the piecewise function. And we can see that here. This has a derivative of 0. This has a derivative of 1. But let's show that. So f prime of x equals derivative of cos is minus sine x, and derivative of 1 plus sine x is cos x. Let's evaluate this at 0. From this side, so this is actually a limit from the left. So we'll just use direct substitution. Minus sine 0 is 0. And from the right, again, we'll use direct substitution. Evaluating this, we get 1. Okay, so it's not differentiable at 0 because the derivatives don't match, so the derivative does not exist. Okay, so because we can't use the mean value theorem, doesn't mean that there isn't a value that we can find. So that's the average rate of change. And we can see that we match here, we match there, and we also match down here. So let's find these values. Analytically, we need to find the average rate of change, so we do f of negative pi. This is cos negative pi, and that's the negative 1. We need to find f of pi. This is going to be 1 plus sine pi. And this is 1 plus 0, so this is 1. So our average rate of change is f of pi minus f of negative pi over pi minus negative pi. So we have 1 minus negative 1 over 2 pi. So this is 1 over pi. So in segment A, we're looking for C such that negative sine C equals 1 over pi. So C equals inverse sine of negative 1 over pi. So this value is negative. So that means we have an answer in quadrant 3 and 4. So we want to find the C prime is inverse sine of the absolute value of negative 1 over pi. This equals 0.3239. Our quadrant 4 answer is 2 pi minus 0.3239. And we have to subtract 2 pi because we're looking on the interval from negative pi to 0. Quadrant 3 answer, this works out to negative 0.3239. Here we have pi plus 0.3239. And then we're going to subtract 2 pi from the whole thing. And we get negative 2.8177. Okay, for the second interval, we're looking for cos C equal to 1 over pi. We get C equals inverse cos of 1 over pi. And we find that C prime equals 1.2469. This is quadrant 1. And our other answer is in quadrant 4, because we have all students take calculus. However, quadrant 4 is outside this domain. So we just have 3 answers. This is 1, this is 2, and this is 3. And that completes this lesson.